Alright, so today we're going to start going over section 1.4. But before we do that, just wanted to let you all know that there are two study guides up. One is available to y'all through WebAssign and the other one through Blackboard, through the course material. Between the two, we cover everything for the exam, which will be next week. Having said that, the exams, typically what I do with exams is give them the last day of the week, just so that you have the entire week to prep for it. Because honestly, who wants an exam the first day of the week, right? Or even in the middle of the week? Might as well do it at the end. So you have time to prep for it and ask me questions, right? So the exam the study guide that's available to you all through WebAssign, it is something like 70 some odd questions, and it just covers everything that we're going to talk about, as well as the study guide that I posted on Blackboard. The study guide that I posted on Blackboard is the end of the chapter, really. It's the study session there. Having said that, I think that's all the announcements I have for y'all. Office hours. For anyone who didn't see, I posted office hours. Those might still change a little bit, just because they run into my professor's office hours. So I might change those just so I can also attend office hours. But having said that, let's get on with things. So, section 1.4. Section 1.4 is really all about the definition of functions. Does anybody know what a function is without reading what this says? What's a function? Function is really just an equation that takes in one value and spits out one value. So for every x, you'll only get one y. And any equation that fits this behavior is called a function. It's really the general gist of it. Having said that, we have this idea of the domain and range. The domain is where all of your x values come from. The range is where all of your y values go to. Make sense what I mean? Yep. So as an example of this, let's imagine we have all of the real numbers. This funny R just means real. We're going to have two bags of them. Our domain would be those real numbers that we can choose from, and our range would be those real numbers that we go to. And our function says, all right, let's take these and send them over here. This is a common diagram that you might see if you're looking at other resources. And like I said, all we're doing is saying, let's take our x values and send them to some associated y value. Notice we could potentially pull from all of the reals, but we have a particular domain within all of the reals, right? Similarly, we could be potentially sending to all of the reals, but we have a particular range that we're sending all of the reals. Make sense what I mean? Another common way of thinking about functions is kind of like a machine. You have some input, a process that you do onto that input, and then some output. It's another pretty common way of thinking about them. Having said that, let's determine if some of these different equations are functions. How are we going to do that? How are we going to determine whether or not these things are functions or not? Yes, absolutely correct. I'm
You're
loving
pretty much
it,
just
guys.
gonna work them.
Say what?
You're pretty much just gonna work them. So like for the x, you put it. So for example, a. For if you want to find the y value, you just put 0 in for x. So then you just do the math, and then you'd find the y. And then if you want to find the x, then you put a 0 in for the y.
Yeah, this is one way of going about it, like that table approach, right? The other way we could go about it is to rewrite these equations solving for y, right? Make sense what I mean? So let's see some of what I'm talking about. So start off with the solving process, right? We take each one of these equations and we solve for y. Hey, notice in two of these though, you have a plus and a minus, right? So this is plus minus, this is plus minus. What does this tell us? When we see that there, what does that say? Yeah, exactly. Like, whatever we put in for x, let's say we put in 1 for x, right? Let's not use 1, let's use 2. Let's say we put in 2. Damn, that's still negative. Alright, let's put in 1/2. Let's go about it this way. Let's looking at b, say y is equal to plus or minus the square root of 1 minus x squared. Let's use x is equal to 1/2. When we do that, then we're going to get y is equal to plus or minus the square root of 1 minus 1/2, that quantity squared, right? Which is going to give us plus or minus the square root of 1 minus 1/4, which is going to give us plus or minus the square root of 3/4. But really, this is two different answers, isn't it? There's a positive, and then there's a negative. This is saying that y is equal to either the square root of 3/2 or the negative square root of 3/2. So there's two answers here. And because of that, this can't be a function. Make sense what I mean? Yeah? So, just looking at what their graphs look like, we can kind of see this, right? Like, let's move along the x-axis. Notice, after this initial point, all of these have two different y values for every x value, right? Yep. Similarly, the circle. So we fail to have this one-to-one relationship. Everybody with me? All right, well, having said that, before we go any further, let's check out domain and range a little bit. How would we determine what the domain and range of different functions are, or different equations for that matter? Yes, sir. Equal it to 0? Yes and no. So, one thing we can talk about, one thing we should start by thinking about is where our domain and range lives, right? It's all real numbers. Agreed? So having said that, in the case of A, we're taking the square root of x minus 1. Well, we know the square root will give us a real number for any number 0 or greater, right? So the question here now becomes, well, when does x minus 1 fit that. What's going to be true anytime x is equal to 1 or greater, right? So we can assume, just from that our domain is going to look something like this, that it's going to have to be for x values 1 or greater. Agreed? And this is generally the type of thinking that we're going to need to apply here. What do we know about parts of these different functions? In this case, we know that the square root has a very particular domain. Anytime, whatever you put into it, isn't negative.
Not necessarily.
If you're considering complex numbers, you're right. But in our case, we're just going to restrict ourselves to just reals. So for this reason, in the case of A, we know our domain is any value, the x value, 1 or greater. There's a couple of different ways we can write this. We can write this as an interval, or we can write this as an inequality. Or we can write it as a set, or so forth and so on. Like, there's a couple of different ways we can express this idea. So we know the domain is going to be any value where x is greater than or equal to 1. What about the range? What's the range of this thing? What values can we get from a square root? 0 or higher, right? Absolutely. Does that change depending upon what we put into it? Like, is that going to change anything here? Not really, right? Because we can get to every number inside the radical. Makes sense what I mean? So we know the range is going to be x in the interval 0 to infinity, or x greater than or equal to 0. Make sense what I mean? So, some more notation. When I write things in interval notation, does anybody know what the square bracket means? Yes, it can include that number. And anytime you see a rounded bracket, it means you go up to that value, but you don't quite reach it, right? So let's say, for example, we had 0 to 1. In this case, we can achieve 0, but we can't achieve 1. So we could be 0.9, we could be 0.99, we could be 0.9999999, we could be Chuck Norris and count nines for infinity, but we'll never get to 1. Make sense what I mean? Go. All right, so another way of thinking about these problems, of these questions of domain and range. Let's imagine we've got a flashlight, and we're shining this flashlight perpendicular to the y-axis, right? Where on your y-axis is the shadow of your graph? In our case, it's every y value above 0, or 0 or above, right? Similarly, we can do the same thing for the x values. And we can find that it's any x value 1 or above. So this is another way of thinking about it. Is like shining a light. Where does your shadow get cast? Everybody cool with this? Go. Having said that, some more notation. we'll oftentimes see functions represented in a very particular way. We'll oftentimes see the notation f of x, g of x, h of x, blah, 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 blah. We can literally pick whatever we want to represent our function with, right? Because what's being said here is we're taking the name of the equation and doing it to x. So f of x is the function of x, but f is playing the role of a name. Does that make sense what I mean? So here, we could write this as x squared. This could be y minus x, or no, let's not use that. X plus 1, x cubed, or x squared minus cosine x, so forth, so on. Like, we could do all sorts of different functions. Anytime I said f of x, I would be talking about squaring it. G of x, I would say, just add 1 to whatever your x value is. H of x, do this, so forth, so on. So really, this f of x, g of x, h of x, whatever, this is just notation to say you have a set of instructions, you're calling it a thing, and you're doing it onto this term that we call x. Everybody with me? Yep. So in that way, if I were to write f of x is equal to 2x squared minus 4x plus 1, now find f of negative 1, I'm just saying do the function when x is equal to negative 1.
That would make it a positive one.
Right. That would make it a 7. Is everybody cool with this? Yep. Dope. So, having said that, why don't y'all try, why don't y'all give B a shot here? See what you come up with.
And you write that on the board, please?
Yeah, absolutely.
Thank you.
Yeah, no problem. So B is f of x plus delta x minus f of x all over delta x. Sorry, it probably helps to know what f of x is, doesn't it? X squared minus 4x plus 7. at it. This probably is going to take a couple seconds, I'll admit. So the first thing we're going to do is we're going to plug in x plus delta x into our equation, right? So we're going to try to solve that or simplify that as much as we can. And then from it, we're going to subtract this f of x, right? Then we're going to divide all of this by delta x. So what does that all look like? All of this together, first thing we're going to do, as you said, is plug in x plus delta x into our function. Then we're going to subtract from this our original function, right? And what we're going to get is this huge long mess of a line. But hey, things are going to start canceling out here. This 4x, it's going to cancel with this 4x. This 7 is going to cancel with that 7. This x squared is going to cancel with that x squared. And what we're going to be left with is this 2 delta x plus delta x, that quantity squared, minus 4 delta x, all divided by delta x. Well, all these terms have delta x in common. Our denominator is delta x, so we can go ahead and simplify this further, right? We can cancel out those delta x's. And when we do, we get that final form, that 2x plus delta x minus 4. Now these notes are already online, so I'm going to go ahead and skip ahead. But the idea here is that whenever you have a function and you want to put something into it, like this x plus delta x, you just literally do that, right? Like nothing changes, the rules don't change. You just go to your original equation every time you see x, you replace it with x plus delta x. Cool? And then the rest of the math works the exact same. Okay, so what about the composition of functions? What about the case where I have an f of x and I have a g of x, and I want to start putting them together in really weird different orders? Well, all we do is exactly like what we did in that last problem. Everywhere we see an x in the original f of x, we just put g of x in there. But g of x has a particular meaning, so we can put that equation in there. Make sense what I mean? So, as an example, let's say we've got f of x is equal to x squared minus 1. Well, let's say g of x is equal to x plus 1. Well, in that case, f of g of x is going to be equal to f of g of x, which is going to be equal to g of x squared minus 1, right? But we just said g of x is equal to x plus 1. Now we're squaring it, and we're going to subtract 1. What we're going to find is that this whole thing comes out to be x squared plus 2x plus 1 minus 1. Is everybody with me? Or finally, just x squared plus 2x. Now question, what if we go the other way? What if instead of saying f of g of x, we say g of f of x? Are we going to get the same thing?
No.
No. No. Not necessarily, anyhow. Sometimes we might, but as a general rule, no, we're not going to. I'll leave that for y'all to do as an exercise.
We'll get the same one.
No, don't. Having said all of this, using again this idea of the machine, right? We can think of it as putting an input into g of x, and then getting that output and putting that into f of x. Which is essentially what we've done here, right? Like whatever g of x comes out to be, we would have solved that and put it in and worked it out. Make sense what I mean? Yeah? So, as another example, doing the exact same thing, right? We take f of x, and we put g in for x. We say, all right, well, I know what f is. Everywhere I see an x in my original equation for f, I'm going to put g of x. And then everywhere I see a g of x, I'm going to put whatever that equation is, right? Whatever those rules are, that function. Put that in. Then I'm going to reduce as much as I can. And just again to reiterate, f of g of x does not have to be equal to g of f of x. And we can see that here, right? Everybody cool with this? How about y'all at home? Good so far?
Yep.
Cool. All right. So what about an inverse function? Well, an inverse function is any function that when composed with the original function would just give you x back. Does that make sense? Everybody cool with this? Yeah? So it's really just undoing your original function. The inverse function is just a function that says, all right, you got to y, now let's get back to x. Make sense? And we write it in a very particular way. We'll use this notation right here. This f superscript -1. And something else to notice. It doesn't matter if you take f inverse of f of x or f of f inverse of x, you're still going to get back to x, right? Like this order here doesn't matter. Because they undo each other. If one undoes the other, then naturally the reverse is true. Right? Just like following a map. If you follow it in one direction to your house, you're going to get home. And if you follow in the opposite direction, you're going to get back to school. It's the same idea as that. So, one way of thinking about it is this sort of ordering, right? Like we do f, and then we do g, then we get back to x. That's really all we're saying here. Now, having said that, something cool happens with the graph of f inverse. The graph of f inverse is almost identical to the graph of f, except for one thing. F inverse is reflection across the line x is equal to y. So think of it like a mirror being held here. If you knew just f of x, the reflection in that mirror would give you f inverse, would be of f inverse. And this makes sense, right? Because what f is doing is saying, let's take an x and go to y. What f of inverse, or f inverse is doing is saying, let's take a y and get back to x. So we swap the order pairs, right? If you put in a into our function and get out b, then when you put in b into our inverse function, you should get out a. And this is why you get that reflection. And that's what they're trying to show you. Put in a into our function, you get out b. You put in b into our inverse function, you get out a. Having said that, just some examples of different inverse functions that we have. Let's say we're given,
It's a snowplow.
okay, snowplow, cool. All right, so let's say we're given any of these functions, right? Each of their inverses would be as such. But it's not enough to just be like, all right, check it out. Here's some functions. These are their inverses. How do we find the inverse of a function? Any thoughts?
Wouldn't you just start putting in for negatives? Like if it's a positive, you start putting in for a negative, and if it's a negative, you start putting in for positive.
Not quite. Yes, sir.
I'll switch the x and the y.
Right. This is one way to do it. This is probably the most common explanation for how to find the solution to the inverse. And I think I know where you were going with that, and yes and no. Depends on the context. So, let's say we're given f of x is equal to, I don't know, let's just go with x plus 1. Well, we want to find f inverse. So the first thing we want to do, swap out notation, replace our f of x with y. Then the next thing we want to do is swap our x and y. Finally, we want to solve for y. Now, question. Let's imagine we want to solve for the inverse function of x squared. After seeing the graph thing, we know, let's start off with, we know the graph of x squared is just the parabola, right? Well, we just saw a second ago that the reflection of our function across x equal to y is the same thing as the graph of our inverse function, right? Everybody cool with this? Well, if that's the case, then our inverse function of x squared would look something like this, right? But if we want it to be a function, it's not entirely true, is it? Because a function has to be 1-to-1. We can only have one y value for every x. And this definitely doesn't have that. So what do we have to do here? We have to choose to restrict our range. In the case of finding inverse functions, we sometimes have to say, all right, yeah, sure. The inverse of this is technically plus or minus square root of y, right? But if we want it to be a function, we have to restrict it. We have to choose to say, let's not take the negative part. Let's just take the positive part. Make sense what I mean? So, F inverse, G inverse in this case, of x is just going to be the square root of x. Is everybody cool with this? Now I show this for a particular reason, because at first I wanted to actually use something like x squared plus 1 or some other crazy equation. Then I realized we have to explain this part. So just really quickly wanted to actually touch on this before I let y'all go do homework and get lost with, but I thought this worked. Yeah, but if it's an inverse function, it also has to be 1-to-1, right? So you sometimes have to restrict the range. Having said that, let's find the inverse function of this example here. We're told f of x is equal to the square root of 2x minus 3. So, applying that first step, we get that y is equal to the square root of 2x minus 3. Swapping out then our x and our y's. Right? So the next step here is to solve for x. Doing that, we find x is equal to square root of 2y minus 3. This implies x squared is equal to 2y minus 3. Which then implies x squared plus 3 is equal to 2y. And 1/2 the quantity x squared plus 3 is equal to y. So finally we get to our point that f inverse of x is equal to 1/2 the quantity x squared plus 3. Yes, sir.
So would you rather us write it how you wrote it up there? Because it also up there, right? X squared plus 30 over 2.
That's actually what I don't know if y'all caught it for a second. Like I stopped to be like, how do I want to write this? That's what I wanted to bring up next. Was going to be how to write this. No, I don't care.
Hi,
Yes, sir.
quick question. So why wouldn't you put the x squared plus 3 over 2 instead of multiplying it by a half? Like, does it matter?
No, it doesn't. That's what we were just saying in here. Is that it doesn't matter, right? Like this 1/2 the quantity x squared plus 3. Well, it's all equal to x squared plus 3 over 2, or we could write 1/2 x squared plus 3 over 2, or a couple other ways. As long as they're all equivalent ways, I don't care.
Okay.
Make sense what I mean?
Yeah.
Cool. What time is it? Enough time, I think, for one more. Well, really quickly, just jumping to the solution of it. We see that, looking at the book, it's the same idea, right? We're going to first replace our f of x with y, swap out our x and our y, square both sides, add 3, divide by 2, and we get to the same endpoint. And just as some icing on top, notice the graph, well, they're the inverse, the reflections of each other, right? Having said that, this is that point I was making a second ago about in the event that we have to restrict the domain. We would say that it has no inverse function properly, right? But it does have an inverse on a restricted domain. Is everybody cool with this? And that's what their point is here, is that you can't, without restricting the domain of your inverse function, you can't technically have an inverse of all functions. Sometimes you do have to restrict domains and ranges. I keep saying domain, I mean to say the range. Having said that, I think I will let y'all go for the day. I'll stick around if anybody has any questions.